Okay, differential equations in context. Surprisingly, derivatives were not made up by mathematicians, so they had something to do while they're high. They actually have a reason for these. For example, you can use them to find some things with like particles. For example, let's say you have a particle graph that just shows the position of something. So it can be here, 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 in a box, for example. So if it was like over here, then it would be in the right. If it's over here, it would be in the left of something. If it was just bouncing like two-dimensionally, that would be position. Then you have things like velocity, which is like miles per hour, kilometers per hour. You're not going to really see a particle going that fast, but that's how you might imagine it for like cars. So those are like your slopes, like how fast it's going to the left or to the right. Then you have acceleration, which is how fast can it increase its mileage per hour, or how slowly does the mileage per hour increase or decrease, while the velocity is changing, if that makes sense. So let's take a look at this question right here. A particle moves along the x-axis so that at time t is bigger than or equal to 0, its position is given by xt is equal to t to the power of 3 minus 6t squared minus 96t. So the first thing tells us to determine all intervals when particle is at rest. So a particle is at rest when v equals 0. So we have to first find v. V of t is the derivative of x of t, as you can see right here. So we go about doing all these equations right here. We have 3t squared minus 12t minus 96. So we need to find out when like the y value is basically 0, when we have to find the t values when the y value is 0. So we just plug that in, and you can get 3 parentheses t squared minus 4t minus 32. That's just it simplified, and that's all equal to 0. And then just from some basic arithmetic, you should know this by now, you can factor it into t minus 8 parentheses t plus 4 is equal to 0, and then you can split that off into t equals 8 comma negative 4. So those would be the two spots where a particle is at rest. However, this model is only for when time is larger than or equal to 0. And because this is negative 4, the particle is only at rest at t equals 8. Okay, now we have to determine all the intervals when x of t is speeding up. So we've already found the v of t, now we have to find the a of t, which is the acceleration. So a of t, just like v of t, is just v of t primed, basically. You get 6t minus 12. So if I zoom in right here, we have these two graphs that model the v of t and the a of t, which I didn't write what it is, but it is 6t minus 6 parentheses t minus 2, or 6t minus 12. So a particle is speeding up when the a and t and the v of t share the same sign on the same interval. And a particle is slowing down when the opposite happens. So we want to see when is it both positive and when is it both negative. So let's look at this one right here. Because it is an even function, it will be shaped like this, right? Like a U-shaped. If it was negative right here, if the leading coefficient was negative, then it would be upside down in like a little N shape. But since it's not, it's just a U shape. So that's why it goes up to down. And those zeros is when it crosses into the negative, right here, as you can see. So we start out positive, and then at negative 4 we become negative, and then to 8 we become positive again. And then the same thing happens for this one. This is an odd function, so it's going to start off negative, and then it's going to end positive in like an arrow like this, right? You might think of x to the power of 3. It's kind of shaped like this, but either way, it starts out down and then goes back up. So it crosses the x-intercept right here at 2, and that's when it goes from negative to positive. So right here, from negative 4 to 2, both of these are negative. And that counts as them being the same sign, which means that it's speeding up right here in between negative 4 and 2. In addition, it's also increasing from 8, because 8 is when it becomes positive here, to infinity. Onward and onward, it will always just be positive. There's no way it's ever going to be negative in these situations here. So just, sleep soundly at night knowing that these will always be positive from 8 to infinity. So if we were to answer that question originally of like what is the interval where x of t is speeding up, it'd be from -4 to 2, union, which means and, 8 to infinity right over here. So that's the two spots where you see this happening. Okay, acceleration and velocity in relation to graphs is a little bit different, right? So I have it shown right here whether it's speeding up or not speeding up, but this is the most important rules to remember, these four. Acceleration is positive when it's concave up, acceleration is negative when it's concave down, velocity is positive when line goes up, and velocity is negative when line goes down. So right here, it is concave down and it is going down. So this is where it'd be speeding up. Right here, after this point of inflection, it's all concave up, but only here does it actually start increasing again. So this is the only part where it'd be speeding up. It's still increasing, but after this point of inflection, it becomes concave down again. So that's why this part isn't highlighted, because it's concave down. But after right here, it starts going negative again and going back down. And since it's negative and concave down, it's speeding up again. It's just speeding up in the opposite direction. Another important thing to remember is that if velocity is negative, something is going to the left. If velocity is positive, it's going to the right. Okay? So if velocity is negative and acceleration is negative, that means that it's going to the left and it's speeding up really quick. And the same would go for the right, just switch the signs. All right, let's talk about an example of a rate in, rate out equation. So let's say we have this question right here. During the time interval 0 to 15, basically, the amount of water in a tank in liters can be modeled by the differential equation m of t, where t is measured in minutes at time t equals 3. There are 37 liters in the tank. What is the best interpretation of the statement m prime of 3 is equal to 25? So my best answer for that would be the amount of water in the tank is increasing at a rate of 25 liters per minute when t equals 3. So I added this liters part because this is our y, right? This function right here is basically saying if I had, for example, if I was 3 minutes in, all right, I would have 37 liters in the tank. That's just giving us our y value. But if I wanted to know how much the water rate is increasing, like how much is going to be going up, the liters entering the tank per minute, I would have to find the y, or the m, specifically m prime of this. That's why we have an m prime here. That's the per minute right here. Per minute comes from this. This is why it's measured in minutes. It's just y over x, because as we know, the derivative is just basically the slope of an instant point. So when t equals 3, because m of 3, t of 3, the amount of water in a tank is increasing at a rate of 25. 25 comes from this. Liters comes from this. Per minute comes from that. So it's very important that you read the equation fully. Now let's say we have another question. A tank has 200 gallons of water in it at time equals 0. Water begins to be pumped in starting at t equals 0. At the same time, a leak opens up and water drains out starting at t equals 0 as well. So it can be modeled by two equations. We have water leaving the tank can be modeled by f of t, which is equal to -9 parentheses 1.04 to the power of t plus 23, where f of t is measured in gallons per hour. This is important, so remember this. The total amount of water in gallons that has been pumped into the tank after the pump was turned on can be modeled by z of t is equal to -216 parentheses 0.92 parentheses to the power of t plus 216. So if we're trying to find in the rate of water increasing and decreasing, we'd have to find the derivative of just one of these, specifically z of t. This is because our unit is in gallons and not in gallons per hour as it is over here with f of t. That's why I have the derivative of z of t here and not of f of t. That's why it's blank. So let's say we want to find a specific one, like we're 19 minutes in, we want to see what the rate is. So we'd put in z prime of 19 minus f of 19. We'd get these two numbers over here, super long chain. I don't want to say them. You want to round them to the 1,000th place, which is 1, 2, 3 points after the decimal. Please, please, please do so, or else you might really screw yourself over when it comes to an actual test, because if you round to the hundredths or to the 10th place, which is to 2 or to 1, you're going to really screw yourself over. You're not going to get the points for something, possibly, even though you got all the work correct leading up to that. Okay, but I got negative 0.344. And the way you'd interpret that is the amount of water is decreasing at t equals 19 minutes, because z prime of 19 minus f of 19 is equal to negative 0.344, which is less than 0, right? Negative number usually, most often, means number go down, line go down, and in this case scenario, amount of water in tank go down. This is basically everything you need to know about derivatives in context. Of course, there's more context that you might see, for example, with your calculator. But I will go over that in a second. But, expect to see something like this on like an AP test. Now let's talk about that calculator. So sometimes the equations that you have are going to be really long and you're not going to want to do them at all. For example, this one right here, 2 sine parentheses 0.55 x squared at x equals 1. Sure, I could do that all by hand, but let's be honest, do you really want to do that? The answer is most likely no. So let's say you have a TI-84 plus CE like I do. You want to press the math button. You want to go all the way down to number derivative parentheses, or you can just press 8. Watch as I do that. And you will get this thing right here. D over D something, parentheses, yada yada, square equals, fill in the blank. So, since we just did this one right here, let's put in the derivative of z at 19. So let's take a look at, what was the original equation? Negative 216, parentheses 0.92, power of t plus 216. So, I'm going to replace t with the variable x. You could do alpha t, but you're saving yourself a lot of time if you do x. You're pressing one less button. So let's type that number in. Negative, this is the button for negative, negative 216, parentheses, 0.92, parentheses, to the power of x, and then that plus 216 is equal to, or that would be it. I got a bit ahead of myself. Now, if we want to find it at 19, you go to this little box over here, and you just simply type in 19. You enter that number in, you get 3.69396471, and if we look all the way over here, same number, okay? That's how you'd go about finding it for a TI-84. I'm not too sure how you do it for Desmos or like all the other things. This is probably the easiest way you can do it. It's really just plug and play once you get good at it. I wish you luck on whatever test you may be taking AP-wise for AP Calculus.